Welcome back to our biomass class, where we're delving deeper into the fascinating world of conversion of biomass resources into heat and power. This video was made with the support of InnoEnergy. Remember that this biomass energy course has 9 lessons. Lesson 5 has an introduction and several videos that go deeper in some applications of biomass combustion. After studying biomass systems for heat and power generation, let's delve into mass and energy balances. Let's start by studying how to manage biomass composition to calculate mass balances. Biomass includes a wide set of materials from different origins. Let's focus on lignocellulosic solid feedstocks. Lignocellulosic materials are mainly composed by cellulose, hemicellulose, and lignin. Very complex organic compounds. They also contain water and mineral matter. Because this complex chemical composition, these solid fuels are characterized using the elemental analysis and the proximate analysis. The elemental analysis provides the information about the mass percentage of carbon, hydrogen, nitrogen, oxygen, and sulfur. The proximate analysis provides the information about the mass percentage of moisture and ash, among other parameters. Let's see an example. The elemental analysis of a sample of wood chips is as shown in the table. The proximate analysis gives us the content of ash that we must add to have the dry basis composition. The proximate analysis also provides the moisture content. With these data, we can calculate the wet basis composition. Just multiplying the dry basis composition of each element by 1 minus the percentage of water. Now, we can start to calculate the combustion products for a complete combustion. 1 mole of carbon produces 1 mole of carbon dioxide. 2 mole of hydrogen produce 1 mole of water. 1 mole of sulfur, 1 mole of sulfur dioxide. The oxygen present in the solid fuels is assumed to contribute to form the oxidized compounds. For simplification, nitrogen is assumed not reacting with oxygen. Therefore, to calculate the amount of products, we need to know the number of moles of each component. This is done by dividing the mass fraction of each component by its molar weight. We do the calculations for 1 kilo of fuel. These are the coefficients for the biomass formula. Please notice that coefficients correspond to atoms present in the fuel, not molecules of hydrogen, oxygen, and nitrogen. Stoichiometry is founded on the law of conservation of mass, where the total mass of the reactants equals the total mass of the products. This means that if the amounts of the separate reactants are known, then the amount of the product can be calculated. Let's start with the calculation of the stoichiometric amount of oxygen for a complete combustion. The oxygen needed is the sum of the moles of carbon plus 1/4 the moles of hydrogen plus the moles of sulfur. However, we need to subtract the oxygen already present in the fuel structure. Because oxygen is fed in the combustion chamber, forming part of atmospheric air. We must calculate the stoichiometric amount of dry air for a complete combustion. This only adds atmospheric nitrogen to the formula. For simplification, we can consider that there are 79 parts of nitrogen and 21 parts of oxygen in the dry air. However, the atmospheric air is never dry, it has some humidity. This only adds atmospheric water to the formula. The moles of water in the combustion wet air is calculated using the moles of dry air and the molar fraction of water in the air. The molar fraction of water in the air is obtained by multiplying the saturation pressure by the relative humidity, which is given in percentage of water in the air. All this, divided by the atmospheric pressure. Finally, the saturation pressure of water in air can be calculated as function of the air temperature. These are the reactants of a stoichiometric combustion of biomass with wet air. For this example, we can calculate the number of moles of wet air step by step. and the mass of wet air by calculating its molar weight. With these calculations, we have the amount of oxygen and air needed for 1 kilo of biomass. Remember that the stoichiometric combustion is an ideal case, a point of departure. For ensuring a complete combustion, we need to avoid the formation of carbon monoxide and unburned materials. For this reason, biomass is burned with an excess of air, around 20 to 30% above the minimum air or stoichiometric air. This is known as non-stoichiometric combustion. The excess factor is defined as the ratio between the real amount of air introduced in the combustion chamber and the stoichiometric air. In this example, we use an excess factor of 1.30. In that way, biomass is burned with a 30% more air than the minimum quantity. This only adds more air to the combustion equation. However, it influences the composition of the combustion products, particularly the amount of water, nitrogen, and oxygen in the flue gas. With the previous equations, we can calculate the composition of flue gas, except for nitrogen oxides, because its formation depend on the operation conditions. Let's focus on the production of carbon dioxide. 1 kilo of biomass produces a moles of carbon dioxide. In this example, around 39.5 moles. Multiplying this amount by the molecular weight of carbon dioxide, we have the number of kilos of carbon dioxide emitted for each kilo of biomass burned. Doing the same for sulfur, we can calculate the sulfur dioxide emissions. For the other components, we only need to know the molar fraction. The water contents in the flue gas is the sum of the water formed in the combustion, plus the water content of the biomass, plus the water content of the air multiplied by the excess factor, gives the amount of water in the flue gas. The amount of nitrogen is found by adding the nitrogen content in the biomass converted into gas, plus the amount of nitrogen in the stoichiometric air multiplied by the excess factor. Finally, the amount of oxygen is given by the excess of air. After calculating the amount of moles of each compound, we can calculate the molar fraction. For ideal gases, this is also the volume fraction of each component in the flue gas. Wrapping up. Combustion is a chemical reaction between the fuel and air. Biomass is usually burned with excess atmospheric wet air. Departing from the elemental analysis and proximate analysis of biomass, we can calculate the minimum amount of oxygen needed for a complete combustion. Also the amount of carbon dioxide produced for each kilo of biomass. Further calculations include the addition of the other compounds of air, that is, nitrogen and water. Finally, with the excess air and the previous calculations, we can calculate the composition of flue gas.